So I need a representative from group 1. That was Daisy's group.
Yes. I don't have the feature to annotate on your screen.
But you have how many?
I got
one
this.
of you guys do, right?
I will do it.
Excellent. And as you do it, I would like you to explain it to us. Okay.
Oh, don't you worry about that, Dr. Henry. You know, sit back, relax. I got this.
Well, my feet are already up and everything, you know.
I'm here. Hold on, I can't find the annotate button. Oh, here it is. Annotate. Draw. All right, everybody. So, oxalate. First thing we did is we identified oxalate has a charge of C2O4, and it's 2-. That's the charge that oxalate comes with. Mercury, Hg. Ooh. All right, mercury has, so what we got was Hg2C2O4, right? So, I forgot what we talked about. Hold on one second. Let me look at my paper real quick. We just went over this, I swear to God. Daisy, I'm blanking. Help me. This is what happens to me on tests.
Okay.
Yeah, that's what I thought it was.
No,
So, yeah, so that's what it was. Okay.
no, I know, but I'm trying to explain it. So the charge for C2O4 is 2-.
And we know
So-
that mercury has a charge of 1. So we want to balance that out. So if we have
Right.
a negative charge of 2 and mercury is 1, we know that we need 2 Hg to balance that out.
Right, that's what I was trying to say.
Yeah.
Okay, excellent.
Mhm.
That is correct. We also know that mercury is diatomic. Mercury 1 is diatomic, right? So it just happens to work out perfectly for this problem anyway. So we didn't have to worry too much about it.
Yes, but we also, Dr. Henry, we talked about what would the charge be if it was mercury 2 oxalate, because we were trying to understand it better.
Mhm.
And we determined that it would just be HgC2O4 because the charge would be 2-, and then if we reverse it, then basically it would cancel out. And so it would just be Hg2, because initially I thought would it be Hg4C2O4, but I was going backwards in my head. So yeah,
Okay.
we were understanding the problem, but I get stage fright a little bit.
Okay. That's good. That's good. Stage fright is okay, as long as you overcome it, right?
Dr. Henry, we don't have to put parentheses since oxalate comes from a polyatomic ion.
We don't have to put it unless we have multiples of oxalate. Do we have multiples of oxalate?
No.
Nope, so we don't need it.
Oh, okay then.
Also, if we were to write this backwards, Hg2C2O4, we
That
could
would
just
be
write.
wrong. That would be wrong.
No, what I'm saying is if we were to write it backwards, like if you gave us the equation and we were supposed to name it, we could just write mercury oxalate without the Roman numeral 1. Is that correct?
No, that is incorrect. That would be wrong.
You have to have the Roman numeral 1?
Yes, you have to have the Roman numeral 1 in this case.
Even though if it is just 1?
Excuse me?
Even though if it is just 1?
Yes, even though it is just 1. So there's certain ones that you don't need the Roman numeral for. One of those is silver, right?
Like
So-
silver phosphate. We wouldn't have
Yes.
needed.
That's
Okay,
right.
so that's why that's how the question came up. Because
Yeah.
we were trying to determine,
Yeah.
and then we saw
So-
that you put.
But those are just exceptions. So you have a few exceptions, okay? And we'll be talking about some of those exceptions today, okay? And
All right.
silver is one of them, and that's the one that I've been stressing a lot. Silver, silver, silver. Long as it's silver 1, then it's okay. And the reason that is, right? The reason why you can't say that with mercury 1, because mercury 1, it's abundant, but it's not the most abundant. It's not like 99% of the time it's going to be mercury 1, right? Mercury 1 occurs about a third of the time in nature. So that's 33%. Mercury 2 occurs about a third of the time. And there's also Mercury 4, right? That also occurs about a third of the time. So you can't just assume that it's always Mercury 1. Does that make sense?
Yes.
So let me break it down like this. So Mercury 1 in life, you'll find it happening about a third of the time. Mercury 2, it's 1/3 of the time. Mercury 3 is 1/3 of the time. But silver 1 is 99% of the time. Okay, so most of the time it's silver 1. It's rarely anything else. So because of that, since it's 99% of the time, then like silver 2 silver 4, and I think silver 3, I have to look that one up. Are all going to be less than 1%. Okay, so significantly less than 1%. Added together, they're all going to be less than 1%. So anytime that you're talking about silver, you're mostly talking about what?
Silver 1.
Silver 1. So that's the reason why if you're talking about silver, you just say silver chloride. We know that that's going to be silver 1, unless you tell me it's going to be something different, because these guys don't happen that often. Right? So those, in other words, in real life, those ions aren't very stable, so they don't happen that frequently. Okay, does that make sense?
Yeah, it makes sense to me.
Okay. And so that's the reason why we have to say, you know, for Mercury 1, but we don't have to say it for silver 1. Okay, sorry to go on that tangent. I just want to try to clarify that. Can I erase my Mercury handwriting there? All of this. Okay, so group 2. Group 2 is Andres, Sienna, Edgar, Jane, Victor.
All right, does anyone in my group want to do it? Okay, I guess I'll do it. Okay, here we go. So it's manganese 4 dichromate. So pulling up the periodic table, I just do a quick search for manganese, which brings up Mn. And I know that it's a 4+ because of the Roman numeral. And then looking at the polyatomic table, dichromate is Cr2 O7 2-, which means I just need to have 2 dichromates to balance it out. So I'm just going to type this out because it looks neater. Cr2O7, and then I just put a 2 there. I'll just type this in text. There we go. 2 of those makes 4, balances out with manganese 4.
So I want to know how you're able to type it out with 2 different text sizes. That's pretty cool. I didn't know you could do that.
It's I just use alt codes to make the subscripts because I just like the way it looks.
Nice. Okay, can you drag that over next to the name?
Let's see. For whatever reason, it won't let me drag, but I'll just retype it next to it.
Oh, no, I got it.
Okay.
Okay,
Alt codes, bro. Share your secrets.
yeah. Yeah, tell us these alt codes.
Okay, so if you want to make a small 2, you hold down the Alt key, you type in 832 and then the number. So it's 8322 and it types it as a small 2. But you have to do it fast or else the computer doesn't recognize it.
Okay,
8323, 8324. It's on chat.
And now what's alt on a Mac, okay?
Find a website that converts it for you.
okay. So you said alt 823.
Alt 832, and then the fourth number is the number that you're trying to type, and you have to get it fast.
Okay. Good to know. I never knew that. That's good. Okay. So let's see. Number 3, group 3. Group 3 is Adriel, Alan, Helen, Javi, and Veronica.
Who wants to do this public speaking in my group, or you want me to do it?
So you're volunteering, right?
I hand you the microphone, okay?
Do you want to do it, or?
You could do it.
All right, I got this then.
Yeah, you got this.
So for number 3, we are dealing with this, what we call covalent compounds, which means that these covalent compounds have prefixes. So now, let me see what I need to annotate this. What my group and I ended up having for this covalent compound, we ended up having, let me see, I need to check this back. We ended up having a hydrogen with a 6 because in hexa means 6. If we have with carbon, we ended up with 5 carbons because penta means 5. And hexa means obviously 6 again. So we have a total of 6 chlorines.
Okay. So did you type it up there or am I blind? I don't see it.
You don't see it?
Yeah, it's not showing up. Did you hit return yet? There you go.
I typed it in already.
But you know that you want to put them together, right?
Right.
And we also know that they're going to be lowercase, right?
Yeah.
Subscripts, not lowercase. Subscript. Okay. You didn't try his little alt thing?
No. I have a MacBook, that's why.
Yeah,
Okay.
it won't let you if you try to type it in. You have to type it in the chat box and copy paste it because Zoom is weird.
Okay. So I have to put it in the chat box and then put it in there. That's
Yes.
so weird. Okay.
Good job, Alan.
Not
Good
my
job.
best public speaking, but thank you.
Oh, you did really well.
Okay, group 4. Group 4 is Alina, Stefana, Julissa, Catherine, Neva, and Ramon. Okay, not all you guys talk at once.
Okay, I'll do it. So I just went based off the polyatomic ion sheet that ammonium is NH4, and so I just figured they would be like NH3.
Okay. Yeah, and that's one of the ones that you guys should know. It's one of the common names, NH3. So go ahead and put it up there. And somebody have already done the number 5. Good job. You want to explain it? Whoever typed that in? Okay, do I have to tell you who typed it in? That was Angie. Oh, she stepped out. So somebody from Angie's group, Angie, Brianna, Tucker, and Jocelyn. One of you guys want to explain it while Angie stepped out of the room?
Damn.
Tucker.
I mean, I would, but I'm just like, I'm confused. I'd love to explain it to everybody, but I'm struggling.
Brianna, do you want to explain it?
For number 5, right?
Yeah, number 5. That's correct.
Hold on. Give me a second. Okay, well, we got ammonia. Wait. Isn't it already done?
It's right. I mean, you already have it done, but I need you to explain it because
Okay.
it doesn't mean anything unless you explain it, right?
We got ammonium from like the polyatomic ions chart. So that's
Okay.
to like determine that. And then for the nitrogen, we just, like change the suffix to like "ide," so it's nitride, and that's how we got it.
Okay, so why do I need 3 ammoniums?
Oh, because of the charge nitrogen.
That is correct, because we know that nitride has a -3 charge, and we know that ammonium has a +1, so we'll need 3 of those to sit there and balance it out. You got that, Tucker?
Yeah, but like what the nitride, what makes it the tride? Because I know there's nitrate, nitride.
Nitride is just that single atom by itself, nitrogen, right? So the "ide" means that it's just nitrogen, right? Does that make sense?
Okay.
So like
There's nothing
oxide,
attached. There's nothing.
like for instance, carbon dioxide, right? That just means that there's just oxygen there, right? And so you're balancing out that oxygen, okay? And we use that term "ide." If you notice, it's always at the end of a compound. So it lets us know that it's the end of the compound. And then also "ide" is also usually, since it's also the end of a compound, that's both ionic and also covalent, because this is a covalent compound. You guys know the difference between covalent and ionic?
Yes.
So
Yep.
you want to make sure you know that, okay? This here is a covalent compound. Let me use my spotlight so I get in trouble for not using it. Covalent compound. This here is an ionic compound, right? So, but they both use that term "ide," right? "Ide" just means that I'm only using that element and then as my negative ion, and then I'm using the other element or the other compound as my positive ion, right? In the case of an ionic compound. Okay. Are you good?
Yeah, now I'm starting
Okay.
to see it.
So the I-I-T-E, that lets me know that there's usually an oxygen involved, right? So it's something in oxygen. And so it's going to be a polyatomic ion, right? ITE means that it's one less than ATE. ATE also one less oxygen than ATE, okay? ATE also means that there's some element or some non-metal with oxygen, or some cases metals, in the case of chromate, right? But it has oxygen in it, like chromate has oxygen in it, right? Oxalate, it's carbon and oxygen. So if I wanted oxalite, that would be one less than that. So that would be C2O3, okay? So ATE means that there's an oxygen. So these are used for what we call oxy anions. Oxy standing for oxygen, anion meaning negative charge, right? So they're polyatomic ions that are going to have a negative charge that have oxygen as well. Okay, does that make sense?
Yeah.
Okay. Okay, so let's move on. We have number 6, group 6. Christina, Daisy, Letitia, Nathaniel, and Pedro. Okay, who's volunteering? Or do I need to volunteer somebody?
Well, I do it, but I can't annotate, so.
I need somebody who can annotate. Daisy?
I'm using my iPhone. I don't know how to annotate it. It's
it's really cool. On your phone, it's really, really cool. All you have to do is press the corner, and there'll be a pencil that shows up. You click on that pencil, and you can write.
The corner.
Yeah.
Where's 3 dots?
Yeah, if you go to your 3 dots, it actually should show up there too.
I see raise hand, chat, meeting settings, minimize, background filter.
Go to the left-hand corner. Click on that, and then you should see a pencil.
Oh, I see it. I see it. Number 6.
Number 6.
I cannot zoom in.
I think you can even select text, and then you can type it in. I think so.
It's gonna be huge.
That's all right. We got plenty of screen on the room. I mean, we got plenty of screen on the screen. And then I'll just retype it afterwards to make it sure that it's full.
There's plenty of space.
Am I spelling it correctly? Then the Roman numeral 2 from the 2 on the mobidium. And then oxide from the carbon monoxide.
Okay.
Oops. There.
It was trioxide.
2.
Oxide. Do I erase it? Because it looks ugly.
Is it, you said mobidium 2?
Oxide.
Are you sure? Because that
We
oxide?
did trioxide.
Carbon dioxide? Oh yeah, I was looking at the top. Yeah, it's trioxide. My bad.
Is it trioxide? What is this guy here inside?
You got something a little bit different.
You got something a little bit different?
Yeah.
Okay, so let me give you a hint. I'll see if I can help you out. So what is CO3 called? And what would be the charge on that?
Carbonate.
Carbonate. What is the charge on it?
-2.
-2.
Okay, so we have carbonate and it has a -2 charge. Okay, so, and this guy, let me, carbonate. So what happens if I lose 1 oxygen? What would it be called then?
Carbonite.
Okay, so if I lose 1 oxygen, it would be called carbonite. And that would have CO2, 2 negative. Okay, so is that CO2?
Yeah.
Yeah, and let's assume that it's 2 negative, right? Because
So mobidium carbonate?
It's
carbonite.
Night.
Yes. Okay.
Oh.
Okay, now what would be the charge on it though? On your mobidium there? So
2.
if carbonite, we have 2 carbonites, and so altogether, I mean, how many carbonites do we have down here?
2 negative.
So we know the charge is 2 negative, but how many carbonites do we have?
3.
So we have 3, so that's CO2, 2 minus, CO2, 2 minus, and CO2, 2 minus. So that's a total charge of what if we add them together?
That would be 6.
So -6 charge. Okay. And then if I have 2 mobidiums, right? So we know that it has to equal what? This total charge has to equal what? About equal 0.
It would have to be also 3 mobidium charge 2.
Okay, so you're saying, but this is telling us that we have how many mobidiums?
2.
We have 2 mobidiums, right? So if we have 2 mobidiums, and altogether it has to be a total charge of, you said 6 altogether, right? Is that what I understood?
Yes.
2 divided by 6 is what?
3.
3. So what is going to be the charge on each of the mobidiums?
3. Positive.
So we could say 2 times 3, right? So then that would give me my charge. So then my mobidium Roman numeral should be what?
3.
3.
Yeah. Okay, so mobidium 3 carbonate. Okay, does that make sense?
Mm-hmm.
Okay.
Yeah.
Let me give you guys, can I give you a little bit of idea? So a lot of times what you want to do is, because the polyatomic ion table doesn't have all of the possibility of all of the ions that are there, right? Because we can break it down even further. But the first thing that you want to do, you want to see if there's anybody that looked kind of like them, right? And if they look kind of like them, like in the case of CO2, well, CO2, okay, so let me see what CO3 is, the one that's above it, and see if I have that on the polyatomic ion table, or if it's 2 above it, right? Because then that's also going to be a possibility, right? So, because then I could have hypocarbonite, right? You guys remember when we talked about that?
Yes.
Yes.
So you want to think about the possibilities, right? And so it's kind of like a puzzle, right? So this is just giving you the clues. Now you need to put together the pieces. Okay. Okay, group 1. Back at group 1. What's the name of this guy?
We got
We got tricarbon dioxygen tetrafluoride.
Okay. You said tricarbon dioxygen
Tetrafluoride.
And how did you get that?
Well, first, when I saw this one, I was going through the periodic table, the polyatomic thing like crazy. Then Daisy came over and saved us saved me and said this is one of those try ones, or one of those things where you have to go through the list.
Ah, okay. And we know that because they're all what?
They're all separate. No,
they're not metals.
Non-metals.
They're all non-metals, right? So in this case, these guys are all non-metals. Now, number 5 is kind of the one that could have thrown you off. I was really happy that you guys got that, right? Because number 5, they're all non-metals, but we know that NH4 is ammonium. So that's kind of like the giveaway for that, right? So anytime that these guys are all non-metals, the first thing that you should be thinking about, oh, these guys are all covalently bonded, right? Unless we know that there's ammonium in them, right? Does that make sense?
Yeah.
Okay.
Okay. When I see this, I think of shampoo bottles because, all the shampoo bottles have those weird names, and now I know how to read them.
Exactly. Yeah. Okay. Group number 2.
Okay. Does anyone want to do it? Okay. I guess I'll do it. So first off, I'll just write the answer and then I can explain it.
Okay.
So I got that, and I know you don't have to use the silver 1, but I like the look of it, so I put it in anyways. And so first thing I did when I saw this was, because I know silver is in the transition metals, I looked at the other half so PO2. So when I looked at the polyatomic ion table, I found PO3, which was phosphite, and I subtracted 1 O, so I got hypophosphite, which gets that. And since it is a charge of 3 minus, and there's 3 silvers, that means each silver is a charge of 1. And I just wrote it all out.
Okay, sounds good. Okay, you guys did a whole lot better than you guys did last week. Very impressed. Okay, so since I'm so impressed, right? So Cole, are you going to go ahead and give them everybody who showed up today so far? Go ahead and give them those extra credit points.
Okay.
Okay, and yeah, and hide it to the end. You know, like a little secret there.
Yep.
Okay. So we have a couple of things to go over, right, before we can move on. We need to talk about acids, right? So I'm going to give you guys this nice little phrase first, and then at the same time, I'm going to talk to you guys about your group projects. How are your group projects coming? Wow, that is so good. That means that you guys haven't finished, right? Is that what I'm hearing? Because nobody's talking, so that means it's done.
I don't even know who's left in our class that's in my group.
So I went through and I've cleared it out. So your group should be solid. So those people are technically left in the class. I did that last week. I didn't email anybody because, you know, that's your guys' job. And you guys know how to email each other, right? In the group. Email your group. You can do it via Canvas, right?
Yes.
Okay, so hitting that. You go down to your email, you hit Canvas, and it'll take you down to all your different groups. You click on that group, and it'll show everybody that's in there. And you just keep adding them, and so that you guys can add them completely, right? So, and there are a few of your groups that I've combined. You guys were under, or you were at 3 or under, and so I combined you with other group members, okay? So if you have any questions about that, you'll notice that you may have been in one group and now you're in another. I believe, Avi, you're one of the people. I combined you and Michael's group, I believe. So.
Do you think our group could take one of the songs of the groups that got combined?
No, I want you to have your own song, you know?
Well, we got literally the worst genre.
You want their genre?
We have the, yeah, we have Screamo.
Excellent.
Not really.
Well, thank you, Catherine. I'm gonna put that in my.
I want to be in rap battle group, man. I got spoken word, but I'd prefer rap battle.
Okay. So I ate organic apples despite them being poisonous. And then my other one is, gosh, she is just on top of it. Thank you, Catherine. That means I don't have to type it all out. Okay, so I ate organic apples. Now, ate, A-T-E, I-C. Okay, so let's start with something simple. Sulfate. Sulfate ends with ATE, right? Now, sulfate we know is SO4 2-, right? Isn't that the chemical formula for sulfate? Yeah, no, maybe?
Yes.
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 Now, when we talk about acids, what makes an acid is gaining a proton. Acids they'll have, and let's say, let me explain to you what I mean by a proton. So if we have H+, right, we know that H+ means that what is happening to this hydrogen ion?
Is lost an electron.
It's lost an electron. So if it's lost an electron, we know that hydrogen has only one proton. Is that right?
Yes.
How many neutrons does H plus have? What is the weight of hydrogen?
It has 1.
Okay, so if hydrogen weighs 1, so we know that 1 proton plus how many neutrons will equal 1?
0.
0. So we know that hydrogen has 0 neutrons. So if I'm giving you an H plus, am I donating a proton?
You kind of went quiet near the end there. Can
All right, so if I'm giving you an H plus, am I donating you a proton?
No, you're giving up an electron.
So if I'm giving you an H plus, I'm giving you H plus. So I'm saying this compound, if it gets an H plus, what is it getting?
1 proton.
It's getting 1 proton. Okay, does that make sense?
Yes.
Yes.
Okay, so when we talk about acids and bases, right? Acids are basically, they're called proton donors, right? Because they give up that H plus. So when we talk about acids are going to be giving away that H plus. Now, this only occurs in an aqueous solution. You guys remember that term AQ at the very beginning, right? That means aqueous. Aqueous means it's in water, right? So when you
a reaction in water,
it's a solution in water. It's more of a solution. So, so here we have sulfate, right? If we have H2SO4 AQ, we call this guy sulfuric acid.
Yeah.
Okay. So when we have 8, it becomes ic and an acid. So that's just SO4, right? SO4. And then we've given it those H pluses. Does that make sense?
Yes.
Okay. If we have, what is this guy called?
Sulfite.
If we have sulfite, ITE, yeah, that's right. We use the OUS. Okay, so then we would call that guy, in the case of H2SO3 AQ. We will call this acid sulfurous. Like, I am so furious at you. Acid.
Is
so
it
that
sulfurous or sulfurous?
It's sulfurous.
Sulfurous.
I just add that extra I in it just to,
that made it sound spicy, like sulfurous.
yeah, see, exactly. So I add the OUS and acid. So sulfurous acid, okay? Sulfurous, right? Okay, so do you guys get that?
Yes.
Yes.
Okay. So I have one more. Ide. Okay. So if I have, this guy is S minus, this guy's called what? S2 minus?
Sulfur.
S2 minus is just called sulfur. We don't give it. So what do we call it in a compound? Do we call it just sulfur? We call this sodium sulfur?
Sulfide.
Sulfide, right? So this is the sulfide. So if it's sulfide, then we add hydro and ic at the end. So then we call the acid H2S, AQ. Hydro sulfuric acid. Okay, do you see that?
Yes.
Okay, so let's test this out. Let's see. What if I have let's say we have H3R RSO4 AQ.
Would that be arsenic?
So what would I call it? Arsenic?
Arsenic
what?
acid?
Arsenic acid. Okay. What about H3ASO3 AQ?
Arsenous acid?
What about H3ASO2 AQ?
Would it be hypoarsenous acid?
That's right. Yes, I didn't tell you the hypo part. Good. Good thinking. So if we get to that point where we're dropping down that one extra, right, we call it hypoarsenous acid. So if I had H3ASO5, what is that going to be called?
Per arsenic acid?
Per arsenic. Okay, and what if I had H3AS AQ?
Hydroarsenic acid?
Okay, simple?
Yes.
Okay, it's great. I hear Edgar. Anybody else?
Yep.
With practice, I can get this down.
Practice, I'll get it too.
Okay. You said, I think. Somebody said, I think.
I'm still a little confused on the hypo.
Okay. Okay, so let's see. Let's go here, right? So we know that I'm gonna move these. Okay, so we know that when we drop down to SO2, 2 minus, that guy is called what? So if this is sulfite, SO3, 2 minus, that's called what? Can you guys see where I'm writing?
Yes, I was leaving it for someone else, but hyposulfite.
Well, no, I want to leave it for someone else. So,
Okay.
but you already said it. It's called hypo. So the fact that we lost 1 oxygen after the sulfite, that makes it hypo. Hypo, like hypodermic, right? What is hypodermic? Thermic. Hypothermia.
Hypo as in cold.
Cold, right? So it would be below, well, it would be below temperature, right? So if you have hypothermia, what does that mean? You're below your normal temperature, right?
Yes.
Yeah.
Okay.
Okay.
So
I'm getting it.
hypo, that HYPO means below, right? And so when you're saying hyposulfite, that means that you're below sulfite, which has 3 oxygens. So if you have take 1 away, that means that you have 2 oxygens. Right?
Oh, okay, I see. Thank you.
No problem.
Dr. Henry, do we have lab today?
Yes, we do.
What's that? Sorry.
Yes, we do. So your lab today
Okay.
is actually going to be working with using nomenclature to write and balance chemical equations. So you guys already know how to balance chemical equations. Now you get to sit there and read the words and then write the equations.
So I got to run and pick my kid up from school, but I'll come back for lab. I just wanted to see if we had lab or not.
Okay, sounds good.
Thank you.
No problem. And so when we talk about the acid that's associated with that, that guy is going to be called H2SO2 AQ. That guy is going to be called hyposulfurous acid. Okay.
That's Henry.
Yes.
Quick question. I definitely came back in the middle of a lot.
Yeah.
I try to get here as fast as I could, but so I'm just going off of what I'm seeing on the screen. So does that aqueous symbol instantly make things orous?
It makes it an acid. The fact that you have the 2 things that you're going to pay attention to. It has to be an aqueous solution, right? And I should say, it should be an aqueous solution, and it also has the H2. Okay. Now there are going to be some acids like citric acids. When we talk about carbon acids, right? Carbon acids are a little bit different, and so the definition of them are going to be a little bit different, and you'll learn that. But the thing about it is that they also have the proton to donate, right? So when you put them in solution, they'll become that acid. Okay, does that make sense?
Yes, but as far as like right now, like on screen, that has to have an H2 or above in order for it to be considered acid with the aqueous symbol?
Yes, that's right. So it has to have an H, at least 1 hydrogen, right? So that, and you put it in front. So when you put that hydrogen in front, okay, so you already know that, well, sometimes it comes in front with it. If it's in front and it has an AQ in it, that may basically mean that you're working with an acid.
Okay, and that's the reason why on the left is still regular sulfite. Okay.
Yeah.
Okay, thank you.
Because this is what we're starting off with. This is so when we separate the acid. So what happens is one of the reasons why it's called a proton donor. And I haven't really talked to you guys about this part is. So when you put an acid, soon as it hits that aqueous solution, or as soon as you boil, because you could bubble this, because you could have hydrogen, dihydrogen, sulfide, tetraoxide gas, and you can bubble that into water, and then you're going to make sulfuric acid, right? And that's typically how your acids are going to be made, or sometimes they'll be made by reactions. Now, this guy, what happens is that it breaks up into its ionic components. It'll break up into this H plus, AQ, meaning in water, and the SO4, 2 minus. Also in water, okay? So it does that almost instantaneous if it's a strong acid. If it's a weak acid, it'll stay in this form, it'll stay connected. Strong acids like to break up. Now, when it breaks up, that means that this guy is a strong acid. It can do damage, right? Because that means that this guy is going to want to connect to something. The first thing that it connects to is the water that's in there. And so it'll actually form another ion called the hydronium ion, which is H3O plus. Since it's in water. But since it's in water, we want to try to keep track of everything, right? And it's a lot harder for us to sit there and keep track of that being in water. So we write it this way to make it easier for us to see, to keep track of the number of hydrogens that we have. Does that make sense to you guys? Or is it just muddy in the waters?
It makes a little sense.
Okay, so, and this guy, so that H3 plus, now this guy, it's kind of reactive. It wants to do stuff, right? So since you have those hydrogens, and if you get a high level of them, they're going to want to do stuff. And so they're going to want to do something with something else. And so they're going to react, right? And so a lot of our strong acids, they're used to, dissolve bones and dissolve or react with metals, or, so they're going to be able to sit there and try to do things because it has that hydrogen ion available to sit there and initiate, okay? Burn your skin, right? So that when you spill acid on your skin, if it's a strong acid, it can burn through your skin, right? You guys like keeping your hands, right? No,
Yes.
You don't?
Yeah.
Okay, so I guess, man, y'all don't like your hands either, so. Are you there?
Yes.
Okay.
I think someone had a question when you were going over the hydronium and how it likes to attach to other things.
Okay. So who had a question? Hello?
I had a question, but I totally forgot about it. Oh, yeah, I got it back.
Okay.
Oh, how do you do just H and F?
Oh, that's a good one. H and F?
Yes.
Okay. So if we have this guy, HF, AQ, what is it going to be called?
Hydrofluoric acid.
Okay, this guy's going to be called hydrofluoric acid. Okay, so that's called hydrofluoric acid. Now, what happens with hydrofluoric acid? Hydrofluoric acid is one of these acids that's a special case. It's considered to be a weak acid. It's not a strong acid because, and I'll give you some definitions of strong acids and weak acids here in just 1 second. Hydrofluoric acid is considered to be a weak acid because it doesn't like to separate. You see how I separated the sulfuric acid up here? Hydrofluoric, because fluorine is it's like an abusive partner. Fluorine's a bully. We've kind of talked about that. It takes what it wants. It makes everybody do what it wants to do, right? I made that statement a few times before. Do you guys remember it at all?
The bully?
Yes, fluorine's a bully, right? So
Yeah.
fluorine's a bully, right? So since fluorine is a bully, fluorine is kind of like that abusive boyfriend. that tells hydrogen, you can't go anywhere. You're going to be with me all the time. Like you go to a amusement park or something like that, and you have to stand right next to fluorine because fluorine's a bully, right? So it doesn't want to separate. Where hydrogen is like, a free spirit, and it's like, hey, I want to go on all by myself. It's not going to let it. So majority of the time, like 99.999% of the time, it's going to stay together. It's not going to separate. And since it doesn't separate, that makes it a weak acid because the hydrogen is not able to sit there and be free like it wants to be. The hydrogen ion. And so you're not going to see these guys too often. So this guy is going to be existing most of the time, and it's not going to separate into those terms later on. Okay, where in this case, this guy isn't going to exist very often, but them separated are going to exist when you're put it in solution, when it's in water. Okay, and which these guys are in water. So soon as it gets the opportunity, it's going to separate from each other. Does that make sense?
Yes.
Okay. Now, because these guys separate from each other very strongly, right? They're very fast. It's considered to be a strong acid because it separates into the hydronium ion, this H+, and then also the sulfur. Okay. Where this guy is considered to be a weak acid because it does it so well. But it still exists as it's considered an acid because we still call it hydrofluoric acid just by definition, even though it's going to try to stay together most of the time. Okay. Now, the only time that typically you'll get these guys to separate is if you exchange partners. So basically, fluorine says he finds a cuter girlfriend, right? And dumps hydrogen. Okay. So does that make sense? And we'll talk about that later on.
Okay. I have another question.
Yep.
Why you didn't put hydro in front of sulfuric acid?
Because it has oxygen, right? So anytime that there's oxygens here, right, you're going to put hydrogen. You're not going to put hydrogen in front of it, right? So you're never going to put hydro. The only time that you use that hydro, ick, is when there's no oxygens there. Like here, we use hydrosulfuric acid, right? So what do you guys think this guy is called?
Hydrochloric acid?
Hydrochloric acid. Okay. And then this guy.
I'm sorry, Dr. Henry, you said you only say the hydro when there's oxygen present. Which one?
No, when oxygen is not present. You see
when
the
it's
oxygen
not present. Oh,
that's
okay.
right. Yeah. Yeah, that's the thing about Zoom. If you break out at a certain point, you get the wrong information, right? So what about this guy? What would that acid be called?
Fluoric acid.
That's right. Okay. Piece of cake?
With practice.
With practice. Okay.